Hello and welcome to this session, and in this session we will talk about the control of VSC through hysteresis switching. Now this part is for the editing people, including the teaching assistants. Here we had talked about this hysteresis control, but we had not covered in week 3. Rather, we are covering it here. So but we have already recorded these things, so therefore we will actually have to insert this hysteresis control in this week after the Clark and Park transformation. So after we have done this DQ modeling, small signal, this is for the TAs, DQ modeling, small signal analysis, etc. we have already done. After that this hysteresis will come in. So this is something for the TA. Now let me go back and start from the beginning once more. Just hold on. Hello everyone. So we are now starting a new session on control of VSC through hysteresis switching, and here we are in the 5th or 6th week of the lecture. And as I told you in a previous one of the lectures, we had skipped this hysteresis control, and we are going to introduce you it here in this week because after we have covered the Clark and Park transformation, then only you will be able to appreciate what we are going to do. And so we have just reordered a little bit, and we have put this hysteresis control a little bit later into the course. Now, what is the content of today's lecture? In today's lecture, we will see the hysteresis PWM switching strategy and a simple control of the VSC using only Clark's transformation. We will not use the Park's transformation. And this is one of the easiest switching and control technique of the VSC. Also, of course, it has some drawbacks, but it is one of the easiest things to understand. So let us see what is this technique. Now, this hysteresis switching of the PWM rectifier is very popular technique. As you can recall that this VSC can be used in a variety of applications, grid support, EV charging, like that. And in many cases, when you do not need some advanced control, hysteresis PWM switching is done. It is very simple to understand and easy to implement, and no controllers. So you do not need any PI control for this. So controllers are not needed here. So what is basically done, we can understand this by a single phase VSC. It is the same thing for a 3-phase VSC, but it is very easy to understand with a single phase VSC. Now, in this scheme, the current which is flowing through the converter is forced to be inside a band by continuous switching. So this current here, which is flowing through the grid, this is forced to control, to inside a band. So for this to happen, for example, in this converter, as you can understand, the DC bus voltage should be higher than the peak of the AC voltage. Remember that this DC bus voltage is going to should be higher than this voltage here. If you do not have this condition satisfied, then the hysteresis switching will not happen. The reason being that if the DC bus voltage is lower than this point's voltage, then the the diodes will conduct as if it is an uncontrolled rectifier. Okay, so basically you need to control the current with the help of these 4 switches T1, T2, T3, T4. Okay, so you have to increase or decrease the current at your own will. Okay, as per your specification, you want to increase the current or decrease the current. But if you have a diode bridge, you cannot control. So therefore, in order to do this, the DC bus voltage must be more than peak of the AC side voltage. Okay, this is important for it to happen. So on looking it in another way, you can also think like this T1 and T4, this is nothing but a buck converter. Okay, because the output voltage VAO say is always less than the input voltage, right? So in that way, if you think this is a buck converter, right? So the DC bus voltage must be more than the peak of the AC voltage. Okay, now what are we doing here? So suppose the actual current here, this is the current which we want to control, and this current is shown by this this line. This is the actual current. Okay, and you can see here this current is being forced to be inside a band. Okay, this band of current is called the hysteresis band. So what is there in the band is that there is an upper limit to the band, as you can see here, and there is a lower limit to this band. Okay, and whenever this actual current, the red one, whenever it hits, suppose it hits the top one, okay, the current is forced to go down. You can see here the current force is forced to go down here, and it hits or the lower boundary. Okay, the lower boundary of the band. When it hits the lower boundary of the band, it is again forced to go up. Okay, so in this way the current always is within the band, right? The current is within the band, it is hitting the lower boundary and then it is going up and hitting the upper boundary, again going down and going up, right? So with this strategy, therefore, we can actually follow the reference current. So this is the original reference current. Okay, here is the reference current. As you can show here, this is the reference current. This reference current is being tracked. Okay, in this case we want this is the I star. Okay, this is the I star reference current. We want it to be sinusoidal, right? Because we are dealing with the sinusoidal grid, right? So this reference current is I star, is the which we want to follow. So this reference current is being tracked. Okay, so there is an upper and a lower boundary to this reference current, and the actual current is following the reference current with a certain error, okay, as dictated by the hysteresis band. Okay, so now how do we control the current to lie within this band? How do we switch the 4 switches? Of course, we have to do this by using these 4 switches which are present here. So we are turning on and off these switches. The current goes up, hits the boundary, goes down, hits the lower boundary, again goes up, goes down, like that, up, down, up, down. So now here you can see the one scheme, unipolar switching scheme. So what happens here is that during turn on, okay, so the diagonal switches T1 and T3 are turned on. Okay, so at first these 2 switches are turned on. Okay, you have a reference current. So this is the reference current here. You can see this is the reference current here. Okay, so the actual current, suppose the actual current is starting to rise. Okay, it will rise now. Why it will rise? Because when you have turned on these two switches, the VDC voltage comes here at this point, and so VDC minus VS is the instantaneous voltage, okay, of the AC side. So VDAC minus VS is LDI/dt. I have neglected to be very small, okay, very small. The resistance I have neglected. You can also use the resistance, then it will become Ri plus LDI/dt. I have, for the time moment, I have used a very small resistance. Okay, so then VDC minus VS is LDI/dt, right? Now, as I told you, VDC is always more than VS, always. Okay, it is the DC link magnitude is more than the peak of the AC voltage, right? So therefore, if VDC is more than VS, so DI/dt is positive, right? So you can see here, therefore the current will rise. So this is what will happen here. Okay, the current from the lower boundary will start to rise. The slope of the current is determined by L. Now what happens is, at the next instant of time, okay, so once the current reaches the current reaches at this point here, the upper boundary. Okay, now there we have to sense the current. So in this technique, we have to always sense the current and see where is the instantaneous position of the current with respect to the hysteresis band. So T1 and T2, so once it reaches the upper boundary, then T1 and T2 are turned on. So then we turn on T1 and T2. What will happen now is that this voltage here now becomes 0, ideal switches. So therefore the inductor current will now free will. Okay, so therefore VDC becomes 0 and minus VS is equal to LDI/dt, right? In this case, therefore the DI/dt, suppose at this point VS is greater than 0, suppose, so then DI/dt is less than 0. Okay, so what will happen is the current will fall. The current will fall. Again, it will reach this lower point, and once it reaches the lower point, again we go back here and the current will rise once more. Okay, so we can alternately use the switches T1 and T3 and T1 and T2. Okay, so during this condition, the current will actually free will also through the diode. Okay, for example, during this condition, okay, T1 and T2 are turned on and the current will flow through this. It will go through like this and it will flow like this. Okay, this is the path of the current when T1 and T2 are conducting and the current instantaneous magnitude of current is positive. Anyway, we will okay, this is how it works. So, and when in the negative cycle, similarly we will use T2 and T4 and also T3 and T4. Okay, this way the switching happens. So as I told you here, if the VDC is greater than VS, the current slope is positive in the first case and negative in the second case, right? So if you now see this VAB voltage, here is the point A, okay, AB voltage. If you see this voltage VAB, then it is, this is here VDC and 0. Okay, it is switching between 0 and VDC all the time, and in the other half, the negative half, it will be switching between 0 and minus VDC when you turn on switches T2 and T4. Okay, so you can understand that this technique of switching is very simple to understand and very easy to implement, because you have just a band, and within that band you are trying to control the current. Okay, there is also other type of switching which is also an extension of this technique, which is called the bipolar switching scheme. And in this way, what happens is, during turn on, so you use these two switches, and so then you have this equation like before. Okay, but when you want to decrease the current, then you use these two switches, so then you have the minus VDC coming. Okay, so again it's a very similar situation. Okay, so but here you don't use the zero state, you use always the two diagonal switches. Okay, so this bipolar and unipolar switching we will explore later when we will talk about this totem pole PFC. Okay, later in the course, and we will see then there are some things here. Okay, we can actually optimize certain things here. We will not talk about it here like right now, but remember, we will again come back to this kind of switching later. Now here VDC is again greater than absolute value of Vs, so the current slope is positive in the first case and negative in the second case. Okay, it's very simple and you can understand what is happening. So the hysteresis control technique is very easy to implement. Now this is important, it's an automatically current control. As long as your reference is within a band, reference is a finite reference you have given. Okay, so you have given something of this kind of a reference, the actual current will always be tracked. Okay, so actual current will always be tracked like this. Okay, so if the reference changes, right, suppose if you have a reference which is changing like this, increased, okay, right, if you increase it, then also it will be able to track here. Okay, you can always put a band here. Okay, so this is the band, this band, inside this band you can control the current. So there is an automatic current control, and this is sometimes very desirable, not only during short circuit but also during overloading condition. Okay, so you can see that if you want to control that, okay, the current output from my voltage source converter, suppose, will never, it should not exceed 110% of my rated current. Okay, you can always put a limit, and the converter will always try to ensure that maximum it is always 110%, and 10% more than the rated current, it will never cross that one. Okay, automatic current control, right? The disadvantage, again, now come to the disadvantage. You can see where is the disadvantage. If you see the waveform, here you can see that during this portion of the waveform, so let me just now clear these things. You can see here, when we do this kind of switching, the switching frequency of the devices are uneven, even within a cycle. So here you can see this here in this area switching is less. Okay, because the current, so here you can see the current starts from here and then goes like this, and then again like this and this. but here the switching is different. Okay, the frequency is different in this area. If you see here, because the band is such, it's a sinusoidal thing, and so it may be switching faster here. Okay, right? So even within a cycle you have a variable switching frequency. So even within a cycle you have variable switching frequency. Okay, so sometimes the switching frequency, so the switching frequency is varying even within a cycle. This is a problem. Okay, this is a problem because the EMI, from EMI point of view, from conducted and radiated noise from point of view, a variable switching frequency action is not desirable. Okay, it will have a wide spectrum of radiated noise, and so this and under certain condition the switching frequency can vary a lot. Okay, so this is not desirable. So this is one of the drawbacks of hysteresis switching. Also, the dynamics, how fast you can control, is also dependent on the AC input source. Okay, the independent P and Q control is possible. I will show you in the next slide that again independent P and Q is possible. One more thing here is that higher is the switching frequency, lesser is the net for passives, but higher is the losses. So here you can understand that suppose you increase the switching frequency. For example, you can see here that take two cases. Okay, in one case the band is larger and in the other case the band is smaller. Okay, suppose if you take two cases here, what happens to the switching frequency? Of course, when you have a larger band, then the current takes more time to travel. On the other hand, when you have a smaller band, the current will quickly travel, right? So which means that if you decrease the band, the switching frequency goes up. Okay, and if you increase the band, the switching frequency is lesser. So this is the design, this is where you have to do a design compromise. If you make your band very small, then you are very correctly tracking the difference. If you make your band wider and wider, okay, suppose a very common example is that you make the band plus minus 5%. It's a total peak to peak change is 10%. So this is very standard. Sometimes people also go with plus minus 10% also. So if you increase the band further, suppose you say no, I will have a band of say plus minus 30%, plus minus 40%, then your switching frequency will go down. Okay, because as you can see here, but you will not be able to track the current so nicely. You will have a lot of harmonics coming in. Okay, on the other hand, if your band is very narrow, you have to increase the switching frequency, and of course then you will have higher losses. In contrary, also you can see that if you have a larger, what happens if you change the value of inductance? If you have a smaller inductance, this kind of switching will happen. Okay, sorry, yeah, that's this last part. You just wait for some time. Yes, so one of the advantages of, again, another increase, so if you increase the switching frequency, your requirement for L also goes down. Okay, this is understood here. You can see here L is lower in this case. So suppose if you decrease the value of the L, okay, what will happen is that if you decrease the value of L, you will move faster, okay. The rise and fall of the current will be faster if your L value is low. On the other hand, if you have a larger value of L, if you have large value of L larger, then what will happen is that the rise and fall of the current will be slower, right? So therefore, which means that if you have low value of L, okay, your switching frequency, so these are inversely proportional, okay. This is also true for any DC-DC converter also. You can recall that the value of L is inversely proportional to the switching frequency, right? So you can here understand that if you increase the value of L, you can actually go with a lower switching frequency, right? So therefore you can see, but on the other hand, if you decrease the value of L, right, you have to have a higher switching frequency, but then you must have higher losses. So the losses in the converter will increase, okay. So with this one, let me also talk about the overall control, how we can use this hysteresis PWM technique in a closed loop system, and recall what we have done as part of the overall control diagram. If you recall, we had a Clark transformation, and after which we had a Park transformation, okay. Now hysteresis PWM switching can be used along with what is known as instantaneous reactive power theory. It can be directly used along with Clark's transformation, and that is what I will show. So we will not go into the Park transformation, and we will use the hysteresis PWM switching to control the converter using Clark transformation alone, okay. So how do we do this? So the grid connected VSC, okay, it can be commanded, as we know, it can be commanded to give a certain active and reactive power, P star and Q star. So this corresponds to a value of IGA, a certain value of the grid current, okay. So for example, with respect to the voltage, I can ask for the IGA and IGB. So this is the IG and this is the VG, okay. So we can actually control the phase as well as the magnitude of this IG with respect to VG, and therefore we can control P star and Q star, okay. So suppose I control that IG with respect to VG like this way, then I can control what is P star and Q star, right? So how do I know what is the reference current, okay, how much to be is obtained, how to know what is the reference current, and this we will use through Clark's transformation, okay. So what is done here is, you can see that we can recall this equation we had derived in the alpha beta frame, okay. The power in the alpha beta frame is PT and QT, right, and this was the equation, V alpha I alpha plus V beta I beta, and V beta I alpha minus V alpha I beta. So with suppose this is the, suppose we should take that this is the current which is flowing, so at through this grid, I can always find out how much is the power, active and reactive power, being injected into the load or grid, okay. So this is in this diagram, how much is the power which is flowing into the grid, I can always know, because I know what is the V alpha and V beta of the load or the grid in this case, and what is the I alpha and I beta which is flowing. How will I obtain it? Here you see V alpha and V beta is obtained, and similarly if you do this one, I will get the Ig alpha and Ig beta, and therefore these are the quantities, right? I will know what is the power being flown or power being obtained. Okay, so then this way we can obtain the actual active and reactive power flowing into the load or the grid. Fine. Now so let me take an example of a statcom. Okay, how to get that reference I star. Okay, because as I told you, if I get the reference current which needs to be flown from the VSC, then we can make this thing work. Okay, so let us take an example of the statcom. So what is a statcom? A statcom is a voltage source converter which is connected. So here is the grid and here is the load. Okay, here is the load here. What does a statcom do? So this point is called PCC, which is called point of common coupling. Okay, what do we do here? Suppose if for the time being assume that this does not exist. Okay, this does not exist. So the grid and the load is exchanging active and reactive power. Okay, and then the load may be absorbing a certain amount of reactive power. This will make the grid operate at poor power factor. Okay, so a statcom is a device which is now shown here. Okay, this is the statcom here. This is basically the whole voltage source converter. What is its purpose? Its purpose is to make sure that power factor is improved. So this is the function of the statcom. So improve the power factor. This is what this VSC is going to do. So what will it do? It will understand first is how much Q load is flowing. So first it will calculate how much is the Q load flowing. Now if that Q load becomes the reference for this VSC, okay, if that Q load becomes the reference for the VSC, then this condition will happen, that the whole of the Q load is being supplied by the statcom, right? So if the whole of the load reactive power is supplied by the statcom, then what happens? The source will not supply any reactive power, and so under that condition power factor will become unity for the grid. So now you understand that how the VSC working as a statcom, or you can say this is also a PWM rectifier also working in a certain way, so that basically the grid sees a unity power factor. The load is absorbing a little bit of reactive power and the statcom is supplying that entire reactive power. Okay, so now the question is how we will get these values. So in a statcom used for reactive power compensation, Q star is equal to the load reactive power. Okay, so we can therefore first calculate, okay, we calculate Q load, and for that we will sense these voltages, we will sense the voltages, and we will do a Clark transformation on this and get the alpha beta component of it. Next, these currents which are flowing, we will also sense that, and we will know what is the alpha and beta component of it. Once we have got this information, obviously now we can see that we can calculate how much is the Q load. Okay, this is the Q load here. Okay, this Q load. So we know that how much reactive power is flowing into the load. Now this statement here, Q load, now becomes the reference for the VSC. As I told you, this Q load is the reference because now I am asking the VSC to supply this Q load. Okay, if I do that, if the VSC can perfectly do that, then the power factor will become unity from the grid point of view. So therefore we can now say that and we know now the question is, next step is therefore finding out the reference currents for the VSC. Okay, I alpha star and I beta star. Okay, so this Q star is nothing but the Q load. Okay, right, this is for the VSC. This equation is for the VSC. Okay, and you can see here in the one, this is the P star and Q star. Here you can see power calculation, and then I am trying to get I alpha star and I beta star. Okay, so this is I alpha star and I beta star. Now in a perfect statcom, lossless statcom, this P star is 0. Okay, because the statcom is not supposed to exchange any active power in a lossless condition. If there is a loss, if it is a real systems are lossy, so then we have to give a certain value of P star so as to take care of the losses inside the converter. Okay, which we will, let us suppose there are techniques, so we will sense the DC bus and we can monitor the DC bus, which will give us the P star. But let us assume that we have a lossless condition, and so P star is equal to 0. So therefore Q star becomes Q load, right? And so now we can do the inverse Clark's transformation. We know this transformation and we have already got these values. These are grid voltage alpha beta components, and we do this, and therefore we know what is I alpha star and I beta star. So these are the reference currents for the statcom, reference currents for the VSC. Okay, so this is where I alpha star and I beta star will be obtained, right? Okay, and now you do the inverse Clark's transformation and you get IA star, IB star, IC star. Okay, so these quantities are sinusoidal. Okay, three-phase sinusoidal. Okay, I alpha star and I beta star are also sinusoidal, but this is a two-phase quantity. So once you have got this one, then you can use the hysteresis PWM, because you are also controlling what is the current flowing from the VSC, okay, into the PCC. So you know what is the actual current which is flowing through the VSC, and you can, so once you got this IA star, so this IA star will be something like this, IA star will be something like this, this is the reference, and actual IA when you use hysteresis will be something like this. So this is your actual IA. Okay, so if you get this IA star, IB star, IC star as I have shown here through what is the load is consuming, so this is the load here. Okay, so based on that we can find out how much is the Q load, and so this we will be able to track. Okay, and we can accurately track this current very nicely using hysteresis PWM strategy. Okay, so now we are integrating the hysteresis PWM switching strategy along with a closed loop control using Clark's transformation. So this is also sometimes very frequently used, and as I can shown, I have shown it here. This is I alpha star, I beta star, and we can use hysteresis switching to force the VSC current to follow the IG star. So this is what is happening. Okay, A star, B star, and C star. Okay, so by using the Clark's transformation only and not going into Park's transformation. So there was, if you remember, there was one earlier we had used a Park transformation, and then we used the PLL, and then we had the DQ control here. Okay, but we have not used, we have bypassed now. Okay, we have directly gone from Clark transformation and going through. So this strategy is actually quite popular in many applications, and the drawback is that the hysteresis PWM is actually going to create a variable switching operation, and the dynamics are somewhat like better in the DQ control. Okay, so this is a technique which I was explaining. And so what are the features of this technique? It is easy to implement. In fact, it is very easy to understand. It is fast enough for many applications, and that is why many applications you will see are using hysteresis PWM switching. In fact, when you are developing one certain applications, sometimes it may be advisable to actually use hysteresis PWM technique, because you have a very tight control over the current. Okay, you can start with hysteresis PWM, suppose using a Clark transformation, and then you move into Park transformation and DQ control. Okay, there is no need to tune PI regulators. Okay, when you go to the grid oriented vector control, you will have to tune the PI regulators, which is not needed. The drawback being that this has a variable switching frequency which causes EMI issues. Okay, so this together, everything was something which we wanted to cover as part of the hysteresis PWM switching strategy. So we will take up the subsequent lectures in the next session.